Hello everyone, my name is Minga Monsia and today I'm going to talk about my project on ferroelectric materials, more specifically how fast they switch and how reliable they are. My project focuses on two kinds of dopants, lanthanum and gadolinium, which are added into a special material called HCO, short for hafnium zirconium oxide. This work was done with the guidance of Professor Tianli Wu. For the background of this project, ferroelectric materials are used in electronic memories, like the kind that save your phone data. They are special because they can remember electric charge, even after the power is off. Hafnium zirconium oxide is one of the most popular new ferroelectric materials because it works well with silicon and can be made very small. And to make hafnium zirconium oxide ferroelectric, we often add dopants like lanthanum or gadolinium, but how we add them and how much can change how well the material works, especially how fast it switches and how much charge it can hold. So in this project, I wanted to study how lanthanum doped and gadolinium doped hafnium zirconium oxide behave and which one works best. My main goals were to analyze ferroelectric behavior, to measure how fast and how much they switch using PE loops, PUND measurements, and NLS fitting plots, and then compare different doped hafnium zirconium oxide samples. In this project, I tested 4 samples, DO4 to DO7. The figure shows the device's basic structure. Each sample has a 2 nanometer silicon capping layer on top to protect the stack, and 2 layers of 10 nanometers titanium nitride electrodes on the top and the bottom, and 9.5 nanometers hafnium zirconium film in the middle, which is the ferroelectric material, and a P++ silicon substrate at the bottom. What makes them different is the dopant type and concentration in the ferroelectric layer. For DO4, we used 3 cycles of lanthanum doping. For DO5, we use 1 cycle of gadolinium doping. DO6 uses 2 cycles of gadolinium, and lastly DO7 has the more gadolinium doping with 3 cycles. These doping cycles control how much lanthanum or gadolinium is inserted into the hafnium zirconium oxide film. Now with PUND measurement, to measure switching correctly, I used a method called PUND, which stands for positive negative down. It stands for voltage passes to the sample and compares the charge when switching happens and when it doesn't. So we can see here that we have the positive up and the negative down. And this way we can know the real switch charge and ignore things like leakage or background signals. Finding the difference of the signals give us a clean delta P, or the PR is the true switchable polarization. And these figures are the example of what we expect to get. And next, to understand how fast the sample switches, I use a method called nonlinear switching model. It fits a curve to our data of polarization versus time and tells us how fast the material starts switching. The key value we get is the time zero, is the fastest switching time. A smaller tau zero means the sample can switch quicker, which is important for fast memory. And here are some results of the measurement. For DO4 is the sample with lanthanum doping. It had the fastest time zero around 68 nanoseconds, meaning it switches quickly, but the amount of charge it can hold, the polarization, was only about 10 microcoulomb per centimeter square, which is low. Also, the switching didn't grow much after cycling, so it may not be very useful for real devices. And next is DO5. This sample had gadolinium doping with one cycle and it performs the best overall. Its switching was also fast. Time zero was about 89 nanoseconds and it reaches a high polarization about 25 microcoulomb per centimeter square. This means it switches quickly and holds a lot of charge. It also improves a lot after cycling. This is called the wake-up effect. DO6 also did well. It has similar polarization as DO5 and a slightly slower time zero around 93 nanoseconds. It switched well but seemed to have more trapping, which can slow down the switching and reduce reliability. And lastly, DO7 didn't perform well. It had very low polarization, only about 3 microcoulomb per centimeter squared, and almost no switching even after many cycles. This shows that too much gadolinium may ruin the material's ability to switch, and there was some issue extracting the parameters time zero, so there's no NL fitting result for this sample. So for conclusion, DO4 switches fast but doesn't hold much charge. DO5 is the best. It switches fast and holds a lot of charge. DO6 is also good but a little slower. DO7 doesn't work well, probably too much gadolinium, so the best balance is with DO5. And discussion. This project shows that the dopant type and amount are very important. Even if two samples switch to the same amount of charge, one might do it faster than the other. DO5 was the best because it had high polarization and fast switching, which are both important for memory. DNL's model helped us quantify the speed in a more scientific way. And lastly, the future work that I plan to do. I'm going to isolate the inner ferroelectric loop in the mixed phase materials, particularly for borderline cases like DO6, using enhanced low voltage measurements, and then extend the NLS model to include the anti-ferroelectric back switching terms for more accurate fitting in samples. And these are some examples we are expecting to get for our future work. These figures are from the paper by Delberg and the new NLS fitting model. Here, using this formula, and this formula is given by the paper by Liu. So thank you for listening. That's all for my presentation.